Welcome back, friend. Now we have understanding of how linear regression works. From our previous lecture, we did a problem which was simple linear regression where there was only one feature which was deriving target variable salary. Now this time in this problem we have three features: the budget spent on TV, radio, newspaper campaign for marketing, and the sales revenue generated from the budgets. So sales revenue is dependent on these three features. So sales is a target variable and TV, radio, newspaper are independent features. This tutorial is divided into two parts. First, we will be re-emphasizing a learning of simple linear regression, which we have already done, and as part of that we will be creating one new feature, total budget, and then we will be looking at couple of distribution, and then we'll be coming at doing simple linear regression to derive how total budget derives revenue. Further to that, we will be also learning about one new matrix which we haven't learned about so far. We have learned only mean squared error, mean absolute error, root mean square error, but we will be touching one more matrix called R squared and adjusted R squared. Once we are done with this, we will be also looking at how we can implement the same performance matrix in sklearn. In our first linear regression problem, we derived these performance matrix through their formulas, but now we will be directly implementing through sklearn. Once we are done with this practice of our simple linear regression and understanding of performance matrix, we will be quickly implementing the same thing but for multilinear regression, where I already talked about this, that how sales revenue is dependent on three features instead of one feature, and we will be also looking at distributions accordingly and evaluate what is generated at the end. So I'll start by going to Google Colab, create a new notebook, naming the notebook. Once it is connected, I can upload the data. So this data set is picked from Kaggle and it is about marketing campaign budgets allocated to different mediums and the sales revenue generated. So first we need to import libraries. We will import a couple of libraries and then we will import as and when we need. So important libraries are import pandas as PD for data upload in data frame and manipulation of data, and then we have import matplotlib dot pyplot as plt and import cpon as sns. Both are visualization libraries which will help us to visualize the data. Let's load the data. df is equal to pd dot read underscore csv. Once we have loaded the data, we will validate the information. So df.info to see how many variables are there. There are 4 variables as we know, and then we also know that Panda automatically allocates data type to the variables based on the values they are having, and as we know the values are in decimals, so Panda allocates float data type. We can also allocate different data type, or we can at the time of uploading or later on. So now we have the 200 entries, and all 200 entries it says are non-null. So let's do some EDA, which is exploratory data analysis. First we will see the range of these features using df.describe, which gives us some statistical measurements like mean, median, mode, and so on. So we have this in place. As we can see, for 4 numerical features, TV, radio, newspaper, sales, the total count is 200. Mean is given for TV budget, which is 147. Minimum is 0.7, which is quite low, and the maximum is 296, and as it shows, standard deviation is quite high, and as we can also infer, there is a lot of difference between min and max. The median is at 149, and similarly we can view for others. Now let's proceed to visualization of data. Maybe we can first see how the target variable, which is sales, is distributed. It is not actually sales, total sales, it is the revenue generated. Now we want to do simple linear regression. So what we will do, we will only need one feature for simple linear regression. Either we can do just to see the effect of one budget, let's say particular to TV, on revenue, or let's create one new feature which is total budget. Okay, and we can create it like something like this, TF, and we can give the name of the new column, budget is equal to DF. We want to sum up all these columns. So in pandas we can simply add up the columns and the corresponding values will be added for each column. Okay, let's have a quick look at first 5 samples using df.head. So we have this budget, total budget, and right now in the first, as part of practice, what we will be doing is we will be deriving the linear regression between budget and sales, and I would encourage you to pause at this point and do it yourself, the steps which are needed. And as a first step, first we will simply see what kind of distribution the sales variable is having. Right now why we are doing exploratory data analysis is just to brush up how we can see the distribution, but at the later stage you will see we will be using this information to do data pre-processing. So let's have a look at the distribution of sales variable, which is our target variable. We can do the same with the help of SNS hist plot. X is equal to data is equal to DF. Let's run it. We can also do KDE is equal to true to see the smoothened distribution, and this is kind of slightly positively skewed distribution, as we can see, because it is slightly the peak is towards left and the kind of tail is towards the right, but it is almost normal distribution, we can say it. We can see a relationship between revenue and total budget, how revenue is impacting total budget. And if you recall, the graph which we use for this kind of numerical relationship is scatter plot. Let's make use of that. Now here we have to specify what we will be having on X. So our X is budget, and on Y we want to see how sales is changing. Okay, and data is equal to DF. So as we can see that there is a linear relationship between these variables, sales and budget. That is, this, as the budget is increasing, sales is increasing. And now we, with the help of linear regression, we have to derive the perfect relation, a best fit line, which gives us, which will help us to predict the value of for a given budget, new unseen budget, what revenue we can expect. To proceed towards simple linear regression, we need to do a couple of things which we have done previously also. What we have done, we have divided it into feature and target variables. So this time our feature is just budget, our target variable is sales. Just note that I have used 2 brackets over here instead of 1. Now let's split the data. So earlier also we have made use of train test split, and in my previous tutorials I have explained why we need to do train test split. What we will be doing, we will be importing the library from sklearn, import sklearn dot model underscore selection from import train underscore test split. Let's run this. And let's split the data. So we will be splitting the data in train test. So we will have x underscore train, y underscore train, x underscore test, y underscore train, and y underscore test equal to train underscore test split. And there we will be passing the original data, original independent and dependent feature, and that how much we want in our test data, we'll be passing that. So let's say we want only 20%, so we'll write 0.2, and to reproduce the result we will be using something called random underscore state, and I have already explained about this in my previous tutorials. So I'll just choose any number and I'll run this. So we have data divided into two parts. The training part, which we will be passing to the model, instance of model, so that it can learn from this data the values, and then we are keeping intact the test data to validate the model. So let's create a model, let's create an instance of simple linear regression. Before that we need to import from sklearn dot linear underscore model. Why I have not imported it in first go is because I wanted to see what kind of libraries are needed when. Alright, so let's run this. So we have linear regression and we have to create a model. So we will create an instance of the model algo which we have just imported, and we'll run it. Now we will train this model with the training data. So for that, what we have to use? Fit method, model dot fit, and to this we will pass x train and y train. So what this is eventually looking at, what kind of distribution is in the data, how the data target variable is dependent on this, and it will derive the linear regression based on this data. And let's see, once we have this, let's run this, and now let's test the model using model.predict. So we have kept aside values and we're just showing x underscore test to it and not the y test, which we know, and then we will be using y test to validate the model. So let's see. Now I'll save this values in a variable instead of just parsing it like this. I'll just save it in y underscore predict. Let's have a look at few more things. Y underscore predict. Let's see a couple of values of y underscore predict by passing it the index from 0 to 5. Let's say we want. Oops, it's not a method. So it has these values. Now we also have in place y underscore test. So we will compare it with the similar values. So we will also pass 0:5 to this. And if you see the first value, this is the prediction, this is the actual value. So this is the prediction, implies that this is the budget, this is the revenue generated prediction for a particular amount of X test, and this is the actual budget which is spent, and similarly other. Now we can, as we can see, there is the difference between these values, right? It's time to do performance evaluation of our model, and we have already learned about 3 metrics earlier, which is mean square error, mean absolute error, and root mean square error. And in our previous one of the previous lecture, we derived these metrics, and we can also make use of sklearn to arrive at these metrics. But before we jump directly into importing sklearn performance metrics and straight away getting these metrics, let's just dive little deep into the results, where I will also be focusing on another very important matrix, which is R squared. And maybe not now, after we learn about linear regression, multiple linear regression, we'll talk about another matrix which is adjusted R squared. Alright, so let's have a closer look on the results which we have got. So let's create a data frame of the values which we are interested in. We are interested in the result of unseen data. So I'll simply create a data frame, df result equal to pd dot data frame. And if you are not still sure why we are doing this, let's just keep on doing and we will understand. Alright, so I'm interested in the result of unseen data, so I'll just create what is my total budget, which is the feature, what is the total budget values for the unseen data, which is test values, and then the actual budget and the one which the model predicted, right? So we have key and value, total budget, and our value will be picked from x underscore test, and what we are picking is the budget column. To make sure what we are actually doing, let's just verify it. So I will run this and I'll run this. df.result head. So if you see over here, I have a column total budget, which is indicating the values just picked from the test data, and what is actually this indicating is the sample number of the record which is being picked from the total records which when we splitted the data. So we have df underscore result dot head. Let's add more values over here. Let's name the column as actual revenue. Alright, so the actual revenue is coming from y underscore test, and predicted revenue which is coming from y underscore predicted. So far so good. Let's run this and let's see what are the changes now. So we have this data frame. We have for the feature value, which is the budget, and what revenue was actually generated for the total budget, and we have the predicted revenue generated. Now we can get a clear picture with the help of this data frame what is actually happening. If you want to reset the index, we can reset that too with the help of something called reset index. And as you can see, the instead of the previous index gets stored in a column called index, and then a new index is generated for each record. So in case we don't want this index, the old index, we can use the argument drop is equal to true. Let's see the result. So we have this, okay, and we can again save this in df underscore result, and again we can see the first few values. Alright, so we have a clear picture over here for unseen data, that this is the budget, this is the actual revenue, and this is the predicted revenue. Now let's visualize these values, okay, on a plot, scatter plot, and we will also draw the best fit line which our model has drawn. So let me give you a task, a simple task to create a scatter plot, two scatter plots actually, to create one between predicted revenue and the total budget, and the other is actual revenue and total budget. I hope you are able to create the scatter plot, and what I will do, I'll create one at my end using SNS scatter plot, and there I have to give x is equal to total budget, y is equal to actual revenue. Alright, these are the points which we already have, and data is equal to df underscore results. Okay, let's see this. Perfect. And then within this plot, what I want predicted revenue, and I want the color as red so that I can differentiate. Perfect. So as you can see, there is these predicted points are on a line, right? We can also visualize the difference between predicted value and actual value, and that is what our purpose is, and that will basically lead us to the performance evaluation. We have done this kind of exercise to arrive at mean squared error and mean absolute error, and this time our focus is the other matrix, which is R squared matrix. But anyways, we need to talk about the difference. So let's do one more thing. Instead of scatter plot for this, let's draw a line using regplot. Run this. Okay, and let's also mark these point as outline as black. Scatter, we can pass the argument in a dictionary. So what we want is edge color. Don't worry about these, you will get through them through practice. So we are right now not talking much about all this. So let's run this. Alright, so we have these predicted values and these actual values, and now what we wish to visualize is the difference between the difference between the actual value and the predicted value, right? And we know the larger the difference, right, the larger this delta between predicted value and actual value, the poorer the model prediction is, and smaller the difference is better the prediction model is. But we are talking in context of all the points, not a single point prediction, right? So first let's visualize the difference. What I'll do, I'll just simply copy paste the code to see the difference, and it is here. Let's not worry about this too much. Okay, so here we are able to draw the difference. If you see clearly what is happening over here, we have drawn the line between the prediction and the real value, and now this difference, which vertical line is indicating, is called residual. Okay, so we have residuals for each point. In our previous lecture we called them errors also, which is effectively y minus y hat, right? Yi minus yi hat, and hat is predicted value and this is actual value, and this is called residual. Residual sum, of course, the sum of all these differences, right? Sum of, we can say, yi minus y hat I, right? Y hat I, sum. And what is residual? Sum of squares is when we square these, right? So this is something residual sum of squares. More the residual sum of square, more is in the variation of the predicted value and actual value, and we are arriving at how good our model is in terms of when we look at the value of residual sum of squares. RSS, residual sum of squares, is equal to sum of yi, which is actual value, minus predicted value whole square. Now let's think about it, that if we closely look at the graph, right, the predicted revenue and total budget, actual values are in thousands of dollars, while we are indicating only the magnitude part over here, right? So if we would have drawn the scale in thousands, this residual sum of squares would have become too huge. So just alone on the basis of residual sum of squares, can we draw goodness of model? We need something which is scale independent, and to arrive at the something, we first need to talk about one more matrix, which is total sum of squares is equal to sum of any value with the difference from the mean of that value square. And let's first draw the mean over here on the same plot. I'm not interested in showing the code how I arrived at this mean line. If you're really interested to know, you can go into the GitHub code of the link which I have given for the whole code, right? But let's focus on what we are talking about right now, which is R squared matrix and how we are arriving at it. So we talked about RSS, right? We talked about RSS, which was residual sum of squares, where we added the difference in the actual value with the predicted value, which is shown by the red regression line, and we summed up and we squared it and then we summed it up, right? Now, why we are squaring it at the first place, I have already explained in my previous tutorial that we are interested only in the magnitude, not whether it is above the predicted value or below the predicted value, right? Now, again, we also talked about something called TSS, which is total sum of square, and which is given by sum of we have a y mean over here now, right? Y mean, and this is y hat, let's, okay, and for individual values we have yi. Now, total sum of squares is at any point the actual value, right, yi, and the difference in the mean, again squaring it and summing it. Now, if you look at TSS closely, it is almost similar to the similar to something we called variance, right? And what we do in variance, we simply divide it with the number of observation to see the variance, and variance indicates the overall variation in the data points from the mean, right? This total sum of squares is almost similar to the variance. So effectively now we have two metrics in place. One is RSS and the other is TSS. TSS is explaining the total variation in the data points with respect to mean. Residual sum of squares is explaining the variation because of regression line, the features which it has chosen. To be more clear, let's say in this scenario we have a feature called total budget, right? And we are predicting revenue. We are drawing regression line, which is basically the best fit line, which is indicating how revenue is dependent on budget, but still we see the difference in the values of predicted actual value in spite of drawing this best fit line. That implies that we might have ignored in our model the features which are also affecting the value of revenue, maybe some festival occasion or whatever, right? There can be many factors. So this RSS is only explaining the variation which is due to features, and there is a delta. And what is that delta? That is TSS minus RSS, which is unexplained by this model. We have a matrix called R squared, which is simply equal to unexplained variation divided by total variation. And you guessed it right, its formula is TSS minus RSS divided by TSS, right? TSS is the total variation. Our model is explaining RSS and unexplained variation divided by TSS is if these points, this line is such that the difference is this difference is as close, that means our sum of residuals, it will be very less. If this is less, this is more, right? As this value decreases, that is when the line becomes closer to the actual points, this value increases, right? So that implies that more the R squared value, mind it that this value will always lie between 0 and 1, right? 0 model is not good, and more towards it is 1, it implies that the model is good. Again emphasizing that higher R squared value indicates a higher amount of variability being explained by our model, and vice versa. So that is R squared. I hope I am able to explain that. And what we started with is we were in need of some matrix which is independent of the scale, and RSS, this R squared is definitely independent of scale and also defining the goodness of model. Alright, so we have talked about the very important R2 square matrix. We already learned about in our previous tutorials mean square, mean absolute square, and RMSE. And now it is the turn to make use of sklearn to derive these metrics. And now what we will do, we will import from sklearn, sklearn.metrics, import mean absolute error, mean squared error, and now we know one more, R2 score. We will be deriving RMSE from mean squared error itself. So let's see. So let's create the variables. MAE is equal to mean absolute error, and to this we will pass y underscore predict comma y underscore test. Similarly for mean squared error, we have mean squared error we will pass to this, and for R2 score we will pass R2 score, and for RMSE, which is root mean squared error, but we will pass one more argument called squared is equal to false. Let's name it RMSE. Let's print these values, and similarly we can do for others. So these are the values, and as we just discussed about R2 score, so if we can see that the values lies between 0 to 1, and currently it is 0.68. And then we can also see that mean absolute error is this one, and of course MSC, which is the squared errors, sum of squared errors, is this one, and root mean square is a under root of this, right? So these are our metrics, and I hope we understand what we are currently looking at. In this, we have not talked about one more matrix, which is adjusted R squared, and which I'll be talking in my next lecture. I'll be just pausing it over here, though it was meant for multiple linear regression, but now I just want to put full stop to the video and want to move in next tutorial, where I'll be talking about multiple linear regression and also one more matrix in regression, which is adjusted R squared. Alright, so let's proceed to our next tutorial.